Okay, so the next unit is image enhancement, and we are actually now trying to improve the image for some visualization improvement in this particular chapter. So far, we only discussed about what is an image, how you can transform it into the transform domain, and derive some benefits out of it. But in this particular chapter, we would like to know how we can improve an image, because you cannot guarantee that every time an image is captured, it is good. So I need to definitely take care of some changes. For example, I would have captured an image at dim light, so illumination may not be good. So is there any way I can improve it? Particularly satellite images suffer from many such issues. So how I can improve or enhance this image for a better visualization? This is what we are going to discuss in this particular unit. Okay, so I the, the slides are visible.
Yes, sir.
Okay, fine. So as you can notice here, there are in fact two different domains in which we are going to operate. We are specifically discussing enhancement in spatial domain and also in frequency domain, because whatever that happens in spatial domain, some equivalent operation would be there in frequency domain. Since I am specifically mentioning frequency domain, we are going to use only Fourier transform here. We are not going to use any other transforms in this particular unit. So the two-dimensional DFT that we discussed in the previous unit would be made use of in performing image enhancement in frequency domain. Okay, so first let us just see what is a in fact what is that we are going to cover in this particular unit. So as I said that there are two different parts of it. In the first part, I'll discuss enhancement in the spatial domain. So here we are going to look at some basic transformation functions that will change an image gray level into another gray level. By doing that, I am going to get an improvement. There is a very important processing called histogram processing. So we are going to discuss about this. Then we discuss a little about how spatial filtering can be done. Just like one-dimensional filtering, we can also do two-dimensional filtering here. So we will discuss about the fundamentals. And when I say there is a filter to be discussed, all of you know that you have what is known as a low pass filter and a high pass filter. So in an image, smooth region is actually the low frequency component and edges are high frequency components. So low pass filter in image processing, we call them as smoothing spatial filters, because edges are high frequencies. So low pass filter will not allow the edges, which means that the image gets smoothened. So we'll discuss about smoothing spatial filters. Opposite to smoothing is sharpening, which is in fact the high pass filter that we are going to discuss. So these are the topics that we are going to cover in first part of enhancement. And then as I mentioned, whatever that we do in spatial domain, some equivalent operation will be there in frequency domain. So we'll also discuss enhancement in frequency domain. That means both smoothing and sharpening operation. The difference is instead of doing it in spatial domain, I do it in the transform frequency domain. Okay. So at the end of this particular module or unit, you should be in a position to choose a suitable technique in spatial or frequency domain to enhance a given image. That means you must pick what is suitable for my requirement. Seeing the image, you should decide whether I should use a high pass filter or a low pass filter, whether I should use some histogram processing or I should use some intensity transformation technique. That means you should be in a position to pick a given technique to perform enhancement. Okay. Now the question is, what is image enhancement? Uh, in fact, the principal objective here is actually to process an image so that the result is more suitable than the original image for a specific application. What I mean by that, assume that you are working on a license plate recognition system. Okay, so you want to recognize the vehicles entering into your SIT campus. So I have fixed a camera near the entrance, and the camera captures the images, and I need to recognize the characters, that digits that is there on the license plate. Based on that, I will decide whose vehicle it is, and then I'll record the time at which the vehicle is entered, and maybe other details, who is the owner of the vehicle, whatever it is. Okay, so your intention is character recognition, and what you need in character recognition is the edges of your character. That means the license plate number that is printed should be very clear. But all of you know that maybe because of maybe a relative motion, that means there is a motion in the, that means the vehicle is not stopping, it is just entering into the gate. So there could be some scaling effect, there could be some blurring, and or there could be some okay, the illumination is not good, probably the vehicle is entering somewhere during the late in the evening, or it may be a cloudy day. So what happens is the image that you have captured, even though it is good, but for my character recognition, it may not be easy for me to recognize the characters. So what should I do? I should improve the contrast. That means I should make it look better compared to what it is. Okay. So maybe I think let me just go to a demo, and after that we will come back. Is the MATLAB window visible?
Yes, sir.
Okay. So what I'll do is I'll just use, I think, I hope I have shown you this. Okay, so this is the GUI that was developed by a group of students long back, somewhere around 2010. So I'll just use one of the technique, uh, may not be this. Okay, so I'll just show you one. Assume that I have an image, something like this. Okay, so assume that I have an image like this. Now, what you should notice here is, if you just look at the gray level values of this image, I think in the beginning of this course I demonstrated this image. I showed that I can not see neither a completely black pixel nor a completely white pixel. Okay, so what you notice is the dynamic range of the image is very less. So we call such images as low contrast images. That means I neither have a black pixels or have a white pixel. I have okay. In fact, carefully observe here. Are you able to see this plot? This plot.
Yes, sir.
Yeah, so this is actually called the histogram plot. What is plotted here is, on the x-axis you will have the gray level values, and if this is an 8-bit image, all of you know that there will be 256 gray levels. So 0 here and 255 here, and what is shown here is the number of times each of the gray level is repeating. So you can carefully observe here in this particular image, uh, you don't have the first few gray level values here. That means the first uh, sorry, okay, so probably from 0 to almost 100 I don't have any gray level here. So that means dark pixels are missing. Maybe from 150, from 150 to 255 I don't have any pixel. So the all the pixels are in fact crowded from probably from 100 to 150 or 100 to 175. So I neither have dark pixels nor have white pixels. So that is noticed here. So you can see that the image is we call it as a dull finished image, or a okay, a low contrast image. Now what I am supposed to do is I should, if I have something like this, if I have something like this, see, observe this histogram from 0 to 255. You can observe that almost all the pixel values are there. I have all the values. So the corresponding image is seen here. All of you will agree with me that the right side image is much better than the left side image. So this could be an image that was captured at dim light or low illumination, or maybe uh, the illumination is improper. But this is an image which is actually better. Okay, so you can see that all the gray levels are present here. I have the dark pixels, I have the white pixels, because of it the image looks much better than this. So this is exactly what we are going to discuss in this course. So now I think probably it would be clear to you. So the objective here is to process an image. Actually what I did is, there is a concept which we are going to discuss in this course a little later, called histogram equalization. So that is how I have improved it. So it is a process. That means image enhancement is a process, so that I make the result more suitable. What do I mean by more suitable? For example, contrast is important for me to have a better look. Okay. Suppose if it is an X-ray image, it is doctor would be very happy to look at the edge information very clearly, because the edges might help the doctor to understand about probably the problem in the X-ray. So that is the meaning of more suitable. I may be interested in contrast, I may be interested in edges, okay, or I may be interested in the number of okay, variations in the edges, pixels, etc. So that is called image enhancement. Input image, I don't say it is bad, but I am making it better so that it is better suitable for maybe from specific application. In character recognition, edges are very important to better recognize the character. So that is exactly the meaning of image enhancement. Okay, and of course it is much problem oriented. Why I say? Because if it is an X-ray image, we are more interested in the edge information. If it is maybe if you want to improve the image for better visualization, maybe the contrast enhancement is better. So depending on the problem, we are going to decide about which technique I am going to use. And as I've already told, there are two different approaches: spatial domain and frequency domain. In spatial domain, you directly manipulate the pixels. So by the name itself, it says you just apply a filter in the spatial domain and just change the pixel values. And in frequency domain, you are going to take the image to the frequency domain. That means take the Fourier transform of the image, then perform something on that. Okay. So one very important point here is, once I do, for example, in this case, okay, if I just ask a question to any one of you, all of you would have told the right side image is better than this. That means you are the deciding factor. Viewer is the ultimate judge. Okay, visual evaluation is subjective. So what does that mean? What is look good to me may not be looking good to some other person. So it is subjective. Because I don't give a number, I don't say that my image is improved by 50% or 60%. There is no quantitative measure I'm going to give you here. For example, in this case, I only said the right side image is better than left side image. Okay, but to what extent is it has improved? Can I quantify it? No. It is only the viewer who is going to judge and say, yes, this is better than this. Okay. So that is why we call it as a subjective evaluation. And of course, a viewer, one who is seeing the image, is the ultimate judge who is going to decide. Okay, fine. Now, what do we mean by spatial domain representation? Well, that means, or sorry, spatial domain enhancement. So let us try to understand this by looking at okay, some basics of images. All of us know that an image can be represented in the form of an XY plot like this. So the notation that is used here is usually the MATLAB notation, because you will show the rows like this, you will show the columns like this. So this is how I am representing. This is the usual representation of an image, because MATLAB starts from here, and the rows increases like this and the columns increases like this. So imagine that I have an image of some dimension, say m comma n. What spatial domain processing does is, it it actually tries to, okay, use a specific neighborhood and take a decision based on the entries in this neighborhood. Okay, so I'll use an operator T, and this operator T will be applied on the original image, and the operator T will be applied, will be on a specific neighborhood, and whatever output I get after applying this, I will just copy it, and what I get is a processed image. So f of x comma y is the input image, t is the operator, g of x comma y is the processed image. So in this case, I can call this as an enhanced image, and this is the original image. Okay, that's exactly what I did here. A simple operation is used. You are going to do it in the next one or two class. So I just took the original image, applied some operation on it, and I got this image. Okay, so f is the input image, g is the processed image, and t is the operator. And as I told, this t, in fact, it is defined over a specific neighborhood. Of course, this neighborhood need not be square like this. It can be rectangular, can be circular also, but usually we make it, uh, in fact, in fact, square for better or easy implementation. But it can be different from square. You can have a circular neighborhood, or it can be an elliptical neighborhood, or it can be even a rectangular neighborhood. Any neighborhood is allowed, but normally a square neighborhood is taken. Okay, now what is shown here is a 3 cross 3 neighborhood. So that means you will see so many pixels under. This is just like a window. So under this window, whatever pixels are lying, look at those values and take a decision based on the entries in this neighborhood. Okay, so as I mentioned already, the neighborhood can be circular also. I can, in fact, have a circular neighborhood, but it is not so easy to implement it. The simplest neighborhood is 1 cross 1. That means I just take one pixel, take a decision based on the value, and copy it as another pixel. Okay, so for example, look at this. Uh, all of you know that the input gray level is ranging from 0 to some maximum. So let us take, this is 0 and the maximum value is say 255. So what is shown here is, this is m is a threshold point. If the input gray level value is less than the threshold, in fact up to this value, whatever may be the input gray level value, I will make them 0. Then near the threshold, I will just start using this particular curve, and whenever the value increases beyond this, I'll make all of them high. Okay, so in fact, when you apply this type of transformation function, I will have some pixels completely 0 and some pixels completely white. That means this will be completely black, this will be completely white, and whatever that lies in near the near the threshold point, they are pulled towards black here and pulled towards white here. Now a very simple way of doing it is this. Okay, now what you notice here is, below m all the values are made equal to 0, above m all the values are made equal to high. Okay, so after I apply this type of transformation, the output image will have only two gray levels. One is dark, other is white. That means it will look like a binary image. I will get a dark pixel or I'll get a white pixel. I'll not get the remaining values. Okay, so this is how we can perform actually uh, uh, enhancement. And what we do is, we take every pixel at a time, and that means every pixel we can say it is a point. That is why this operation is also called point processing. Okay, so you just read the value, take a decision based on the value. Okay, so let me just demonstrate this with an example. Okay, so is the OneNote visible?
Yes, sir.
Okay, fine. So now let us take an image. Maybe I'll just take a 4x4 image, and I'll assume that there are actually 16 gray levels here. Okay, so 16 gray levels means you can have anywhere between 0 to 15 as the entry in the image. How many bits I need to use to represent 16 gray levels? I need to represent 16 gray levels. How many bits I need? How many bits you need to represent 16 gray levels? 2 to the power of what is equal to 16?
4.
4 bits. So you need, that means your gray levels can be from 0 to 15. 0 is represented as 0, 0, 0, and 15 is represented as 1, 1, 1, 1. Okay. So depending on the values, let us just take some okay, numbers here. So assume that this is 5, this is 8, maybe this is 10, this is 2, this is 11, 12, 10, 8, 9, 6. I am just randomly taking some values. Okay. So let us assume that I need to use a transformation function, something like this. So as you saw, the input values are from 0 to 15. Now I will use a transformation of this nature. Up to 7 it is this. Then after 7 it will go to 15. So x-axis is R, the input gray level. This is the input gray level value, and y-axis is the output. Normally this is designated as S, which is operated value. So this is some T of R, and the output will be 15. Okay. Now what is the answer? Can somebody give me what is the answer we'll get here if I do this operation? Simple. This is 7. So all the input gray level values from 0 to 7, I have to copy it as 0. All the values above 7, I have to copy it as 15. So what will be the first one? 0 remains as 0. What about the second pixel? What is this value? 5.
0.
Yes, correct. Then third value 8. 8 will be 15. 10 will be 15, because anything above 7 I have to copy it as 15. 2 will be 0. 11 will be 15. 12 is 15. 10 is 15. 8 is 15. 9 is 15. 6 is 0. 5 is 0. 4 is 0. 2 is, these values will become 0. So you can see that this is a gray level image. What you saw here is a gray level image. It has all the values from 0 to 15. Of course, some of them are missing, that's okay. And this we call it as a binary image now. This we call it as binary image. Okay. I hope you remember uh, in the on-ramp course that you have completed already, probably you would have used a command im2bw. Do you remember this?
Yes, sir.
Yeah, so in fact, this command is what it does, image to binary. So gray level image is converted into binary image because you will have only black or white pixel in your output. Okay, so this is how I can convert a gray level image into a binary image. That means use a threshold, decide. In fact, the challenge here is how to decide this threshold. It's not so easy. I'm just giving an example. So decide a threshold. Anything above threshold, you make it as white. Anything below threshold, you make it as black. So your output is now binary. Okay, so I can just represent it by only using 2 bits now. That means I can convert this into 0 and 1. All zeros are 0, all 15s are 1. So that will become a binary image. Is the point clear how I can apply this type of operation? And this is called point processing, because what I did here is in fact I looked into every pixel, took a decision based on this value and copied it as a new pixel. So this is the input image, this is a transformation function, this is the output image, and you are applying one bit, one pixel at a time, or one point at a time. That is why it is called point processing. Okay, any doubt here? You understand this, the rest of the thing is only to just discuss one by one. Any doubt?
No, sir.
Fine. Now let us look at some basic intensity transformation functions. In fact, the plot that is given here, in fact it covers all of them, so but we have to take one at a time and do it. So what you see here is x-axis is the input gray level, which is R, and it is having 0 as the minimum, L minus 1 the maximum. L minus 1 is decided by the number of bits used to represent. For example, in the previous case here, your L minus 1 is equal to 15 because the maximum gray level is 15, which means I am using 4 bits to represent. So, in fact, it is a 4-bit image. This is a 4-bit image because I am using the 4 bits to represent each of this. So, x-axis is 0 to L minus 1, y-axis is also 0 to L minus 1. If you take this curve, what do you think is happening here? Suppose if I take this curve, what do you think is happening? In fact, it is already written here. What happens? Can somebody respond? Okay, so the first one, if I have something like this is the maximum L minus 1, this is R, and this is S, which is the transformation on R. Transformation on R, this is L minus 1, and it is a 45-degree line. The slope is 45 degree. Slope is 1 in fact. What do you think will happen? Can you tell me the equation for this straight line at least? Output, your y-axis is S, x-axis is R. What is the equation? What is S in terms of R? What is the equation? Guys, what are you doing? Equation for a straight line is y is equal to mx plus c.
S equals to
And
L
since
minus R minus 1.
R, no. What is the slope of this line? 1. So m is equal to 1. Okay. What is the constant? It is a line passing through the origin. What will be the constant?
0.
Yes, correct. So constant is 0, m is 1, y-axis is S, x-axis is R. So what is the equation? Correct, no?
Yes.
So now tell me what happens. For example, if I use this type of transformation for this image itself, where L minus 1 is equal to 15, this is equal to 15, this is also 15. What do you think will happen? If I use this transformation, what will be my output image? What will be my output image? S is equal to R. What will happen? Zero will be zero, correct? S is R.
Value should be same.
Same, you will get the same. That is why I told you it is identity means, okay, I'll not write the other one. So you will get the same image. Output image is same as the input image. So nothing is happening in this particular thing. Only because it has to be given to you, it is mentioned. So this doesn't do anything. This transformation will just copy the input pixel as it is. So identity will not do anything. But this is important. Okay, let me go to that, the second one. Okay, now let us take the second one. This is R, this is S. The second one is this. So this is L minus 1, this is L minus 1. I want you to give me the equation first. What is the equation for S? What is the equation for S? Y is equal to mx plus c. Don't forget that. Y is equal to mx plus c. In this case, m is equal to 1. Minus 1, sorry, because it's with negative slope. What is c? What is c?
L minus 1.
Yeah, L minus? Correct. Sorry. L minus 1. So what is the equation? L minus 1 minus of R. Y is equal to mx plus c. M is minus 1, x is R, y is S, and constant is L minus 1. So this is the equation. That's exactly what I am going to explain in the next slide. So for this, the equation is L minus 1 minus R. Okay. Now what will happen? Can you tell me? As this, if you carefully observe here, suppose if R is 0, my S will become L minus 1. That means L minus 1 is the white, 0 is black. So black pixel will become white. If R is 255, in fact it is maximum, L minus 1 is 255, so your S will become 0. So what will happen? What will you get as output? This is actually negative of an image, right? This will actually give me image negative. That means black pixel will become white, white pixel will become black. So this is how I can generate an image negative. Okay, it is just a simple operation. So let us just discuss that in the next slide. Okay, so the first operation that we are going to discuss is this. See, whenever you are explaining these operations, don't write this complete figure. You have to only write the figure that is relevant to the question that is asked. If I ask you explain image negative operation, just write this curve and explain it. Don't write the entire curve. This is giving you all the curves. Okay, so now what is done here is, as I said, S is equal to L minus 1 minus R, and here L, in fact L is the maximum gray level value allowed. That means L minus 1 is the maximum. You subtract every input pixel value from the maximum. Okay, so what you saw is it is actually going to generate the negative of the image. For example, there is an example here. This is actually a mammogram image. So this image is now negated. You can see that black pixels have become the equivalent gray values here. White pixels have become black here. So even here also there is some white region, there is a black here. So actually this could be probably some medical problem that the mammogram image is having, which is actually in fact very useful. In fact, that is the advantage. You can analyze the breast tissue in the negative of the image very easily. Okay, what you should notice is in this image, this white gray level value is embedded in a dominant dark region. So this may get unnoticed. So suppose if I convert it into negative, you can now see that white looking black and the other regions are white. So therefore you can easily locate the tissue that you have here, the problem that you have here. That could be helpful for a doctor. Okay, so this sentence is very important. Why it is important? Because the question need not be directly asking you to explain image negative operation. That is the straightforward way of asking the question. You can be asked a question something like this: you are given a medical image which is known to have a small uh, gray level region embedded in a dominant black region. Okay, dominant black region. Suggest a suitable enhancement technique and explain. Okay, that is how the question will be asked. That is why I said these keywords are important. Where do we use it? Particularly suited for enhancing white or gray level detail embedded in dark regions of an image, especially when black areas are dominant in size. Okay, so this is a small white region or gray level region, but your dark region is very large, dominating. So in such cases, if you convert it into negative, I can easily locate your white region. That could be helpful. So to enhance such region, we use this negative operation. And I think when you did this on-ramp course also, while extracting the text region from the background, uh, in one place actually this operation was done. I hope you remember. Do you remember that? What was the operation used in the on-ramp course? All of you have completed the course except Praveed. Anyway, look into it. Okay. Suppose if the input is a binary image, I can use a simple operation called IM complement. If I have the input as a binary image, an IM complement operation will make all the zeros as ones and ones as zeros, and I'll get this type of image. Okay, so this is how I can find the negative of an image. Now I want you to tell me, suppose if I apply such an operation for this image, okay, what would be the output? If this is the image, what would be the output? Okay, so I want to do negative. Negative means this is the curve. This will be 15 in my case because this is a 4-bit image. So this will be 15. This is R and this is S. So what is the output? What will be the equation? S will be equal to L minus 1 is 15. 15 minus R. This is the equation for this problem. In general, it is L minus 1. In this case, since it is 4-bit image, it is 15 minus R. So what will be the first pixel? 15, correct? 15 minus 0 is 15. 15 minus 5 is 10. 15 minus 8 is 7. This is 5. 15 minus 2 is 13. 15 minus 11 is 4. 15 minus 12 is 3. 5, 7, 6, 9, 10, 11, 13, 12, 11. Is this correct? Any doubt in this? How I can get the negative of a given image? Any doubt? Or is it so complicated or so silly? Please respond, any of you. Shall I continue?
Yes, sir.
Yes,
Okay.
sir.
Okay.
Yes, sir.
Okay. So this is how image negative can be determined. I think I can show this demo also here probably. Hope I have. Yeah, image negative operation is given to me. I'll take Lerna image, and if I just do negate, I'll get the negative of the image. I hope you can see. These are the dark pixels and they have become the gray pixels here. These are some white pixels, they have become black here. So like this you can convert any given image, okay, into negative. This is exactly what is shown in the slide also. This is a moon image, and if you are interested in knowing probably this dark region which is important for you, you can do it. In fact, you have used this operation in the MATLAB, on-ramp course that you have done. Fine. The next operation is logarithmic transformation. Okay. As the name itself says, I use a log function and calculate the output pixel value. Here also I am applying one pixel at a time. I think it's time for us. It's already 8:48. So what I'll do is I'll just share a link. With this link, apart from taking your attendance, it's actually trying to know what is the status of your um, MATLAB course, not the on-ramp course, the new course that I introduced to you. So the questionnaire will actually ask you what is the status. So that means to what percentage you have completed. So I want you to give that percentage also. The questionnaire is to know where do you stand right now. I'll definitely give you sufficient time to complete it, but just to know what is the percentage that you have completed. So please give your attendance along with this questionnaire that I have asked you. Okay, those of you who complete it can leave the class. And Friday we are going to have the first quiz. I think I have shared the videos, all the videos. I have shared the PPT. So the portions is unit 1.